Um, so hello everyone. I'm Golnaz. I did my master's at the U of A in computer science, and this lecture is going to be an introduction to deep learning models and their applications in healthcare. Um, First of all, I hope you had a restful holiday. And So this lecture is going to be mainly two parts. The first part is the fundamentals of neural networks. So it's going to be a high-level overview of the building blocks of neural networks. And then once you have an understanding of how the neural networks work and what are the knobs and the details and those building blocks in a neural network, in the second part, we'll move to the applications of neural networks. So now that we know how neural networks work in general, on a high level, depending on the data, we can use different types of neural networks that are kind of more well suited for those data types. So it would be either images, or if you have temporally correlated data, like you have some data over the years collected and you want to find a pattern in that, or you're working with text, or you are short of data and you want to do data generation and augmentation. So we briefly talk about some of these applications as well.
Uh,
Um,
Sorry, Golnaz. I think we can see your speaker notes now.
okay,
Oh yeah, now we can see the slide.
okay, then it's fully shared the screen, but I don't know how to, but it's okay, I can
Now,
just,
now it's fine. Now we can just see the QR code.
but if I change
Oh,
the,
oh yeah, it now it changes.
yeah, okay. So throughout the lecture, we're going to have some discussion parts. You can go to the Menti website and then either through this link or the QR code, or directly the code is here. And um, so what I want to start with as the first question is um, So, starting by asking this, what do you think are the applications of neural networks in medicine? It can be either what you've heard in your other courses or in the news or wherever, like the buzzword neural networks you've heard. Um, uh, let's talk about that and like start from there.
Golnaz, do you mind just going back to the slide with the QR code? Thank you.
Brain MRI scans, exactly. So that would be uh, like finding information or like uh, trying to segment a tumor in an MRI scan. Drug discovery. Yeah, that's one of the hot topics these days. Digital twins. Um, I haven't heard of that. What's that?
I wrote that one. From my understanding, it's basically creating a model of a patient in a digital format, basically a twin of a patient, and then testing treatments or maybe looking at their genetic makeup and things like that on that digital model.
Interesting. So kind of a simulator of
Hmm.
as accurate as possible. Interesting. Uh, Informatics, risk stratification. Yes. Yeah. So that information then it can help you to prioritize your choices. Drug discovery, diagnostics in radiology. Complex patterns between variables. That's basically, you can say that's kind of a good definition of machine learning in general. Yeah. Healthcare chatbot. Yes. Yeah. For example, one that could chat with you and remind you to do stuff personalized based on your patterns, or maybe direct you to the right professional based on your symptoms. Yep. Thank you, guys. So yeah, that's a lot of applications out there. So I want to start from what we know from previous sessions. The question is, so we have a bunch of data. What do we want to learn about those data? So how we usually define a problem is that we have a model, and then we have a set of data, and we call them the input to the model or the features. And then based on those features, we want to predict an output. And depending on how the output looks like, you can categorize the problems into two distinct set of problems. So the first one is regression, where the goal is to predict y, and y is a continuous value. So an example of regression would be, for example, predicting the number of COVID cases in the next month based on the patterns in the previous months and all the information that we have. On the other hand, there are classification problems where your goal is to predict a discrete class label. So there's no more an order to the thing that you want to predict. It's just discrete categories. So you want to categorize your data in a sense. An example is a binary question, a binary classification question of, does the patient have COVID based on the sound of their cough or not? So this is a reminder from the previous sessions, and with that, I want to move to the next question, just as a refresher and to make sure we know the difference between classification and regression. So the question is predicting if the patient will be readmitted within 30 days. Is that a classification or regression problem? So imagine you have the data of your patient, of all the diagnostics and all the details, and you want to feed it to a model. So that would be the input to your model. And then what would be the output for a model that's predicting if the patient will be readmitted? You can think of it as a binary response, right? So based on the input data that you have about a patient, the output could be yes or no. So either yes, the patient will be readmitted, or no. So you can think of it as like trying to categorize people into people who are sick enough to be readmitted, or who for whom there's a chance of getting better and they won't be readmitted. Another example on the same topic, predicting a patient's length of hospital stay. Do you think that's a regression or classification problem? So you can think of regression problems. So most of regression problems, there is an order to what you want to predict. It's true that it's not fully continuous in that you can predict in discrete numbers. So it can be a day or 2 days or 3 days. So it's maybe your model can predict like 2.5 days. But it still will be like there still will be an order to things, and you're not categorizing anything, you're just predicting a continuous value depending on the data that you have on your patient. So you can think of many other problems that can either be categorized as classification or regression. And in the previous lectures, you have learned a lot about the general and traditional machine learning models used for regression or classification. So the question here is, we know all these problems, and we already have learned about some of the solutions to either classification or regression or general problems in machine learning. Then why do we need neural networks for? Like, why aren't the previous solutions enough? The answer in general is larger data sets and more compute power. So there has been two major AI ventures in the past, and the second one was really accelerated by more powerful GPUs that could handle the computations that neural networks need. So how neural networks work in general is that they are very good at finding complex patterns and nonlinear relationships. The previous models, they work very well in many cases, but as the data gets more complex, as you get more features, as your data set gets larger and your prediction depends on many more factors, they usually fall short. So when you have larger data sets and high dimensional data, there will be a need for data-driven solutions, and neural networks are one of the best when you have that sort of data. Also, many of the previous solutions that you learn about, they usually work with numbers in an Excel sheet. What if you have unstructured data like image or text? Neural networks can work with that. So that's another reason why we move from previous solutions that we learned about to neural networks. And as I said, the main reason that they work is larger data sets and the fact that we have the ability to make to do all the computations needed to train these models, because usually training them is harder than using the traditional machine learning methods. So with that introduction, let's visit some of the models, some of the neural networks that can help us solve these problems that we talked about. So I want to start with the building blocks of neural networks. And the first building block of a neural network is called a perceptron. And you can think of it as the smallest unit of computation in neural networks. So how a perceptron works is that you have your input data. So here your input data is shown like as x0 to x3. And these could be the features that you've collected about your problem. So imagine you want to make a prediction about heart failure. So you have a data set collected from many people, and you've measured different things about them, like if they have diabetes, if they're obese, you've collected their sex, and all the relevant information. And then depending on them, you want to predict if the person will have a heart failure in the future or not. So the input, like x0 to x3 would be those features. And then the perceptron, what it does is that it makes a computation, makes an output based on those inputs, which is um, a linear combination of all these features that you have. So it would be how you can think of this output is that depending on all of these features and each of them with a different contribution. So one feature could be very important, one feature could be less important, but depending on them, you want to make an output which could be a signal for you or a number that could indicate if the person will have heart failure or not. So that would be how the perceptron basically works. But after this computation, which we call it a linear computation because it's these W's, which I call them coefficients for now, are just linearly multiplied by all these features that we have. But sometimes that's not that simple. You can't make an output just based on the features that you have and assigning an importance to each of them. So what this system needs as a next step is an activation or an activation function. So what that means is that you have all those inputs and then you assign a weight to them, which indicates how important those features are. And then there's also a scalar value that you add, which is called bias. And then once these calculations are made, they should be forwarded to an activation function where its main role is to add nonlinearity to your problem. So that means that once you measure your output, it's no longer just a simple linear combination of all those features that you have, but you're defining something that's making the output a more complex version of just the sum of the input features that you have. So the goal here is that I'm not talking about the training process yet, but once your model has learned from your data, which we call the training process, what we hope is that this output will be as close as possible to the reality. So that means that what we need to do is to adjust all these weights and like find the right importance for each of the input features that we have. So how you can think of these weights is they are a system of knobs that you can manipulate to optimize your model. And by optimizing your model, I mean training the model so that the output that it predicts is as close as what you have in your data set, as what you have seen before in your patients, if they have a heart failure or not. And in general, you can think of weights as indicators of how important a feature in your data set is. So here, imagine each of these features, again, are different characteristics that you've gathered about patients on the heart failure problem. And if, imagine if W1 is the largest one, that kind of means that this feature, the first feature, is playing a more important role in deciding if the patient is going to have heart failure or not. So basically, it's a set of computations that we've set very carefully. So, for example, for activation functions, there are different activation functions out there that, depending on the problem, the person who is setting up the neural network should decide to choose the right one for the problem. And then you also have your weights, which you can think of as knobs that are set randomly at the beginning. So you don't know how important each feature in your data set is, but your hope is to learn the right weights for each of your features by the end of the training process for your neural network. So imagine that this is the system that we have. This is the neural network that we have in the simplest way. And we usually start with random weights. And By random, again, I mean that because we don't know how important each feature is, we just set them randomly from a particular distribution. And so that there is no bias in saying which feature is more important than the other. And once we have that, our goal for training the neural network based on the data that we have should be to change the weights and adjust the weights in a way that can minimize the error that the neural network makes. And by that, I mean, I want the output of my neural network to be as close as possible to the reality. So I define that as a mathematical notion. So here we have cost function. And again, it means that we have the output from our neural network, and then we also have the actual output in the data set. So suppose you've collected data for, let's say, 100 people on heart failure, and you're training the model on those data. And what training means is that, and we're doing supervised learning, so it means that we already have the information about if they will have heart failure or not, because it's a labeled data set. And we go through each of, so the neural network through the training process goes through each of these samples and makes a prediction, and then we can calculate how that prediction is close or far off from the reality in the data set. And then based on that, we can adjust our neural network. So that's basically how we can train a neural network. So yes, we have the cost function. It represents the error between what is predicted and what is expected in the data set. And the goal is to minimize this cost, or loss function, they also call it, so that once we have minimized the cost, then we can say that our neural network is predicting as closely to reality as possible. So it has learned the patterns. And again, there are a lot of like subtleties and details to all of and each of these concepts. For example, depending on your problem, you have the choice of different loss functions in the papers that you read in AI and healthcare. You might encounter some of these names, so I just have them in case you see them and they're not alien to you. But again, for each of them, like there are many loss functions, and one line of research in machine learning could be to find a better loss function so that it could be more easily minimized and like faster minimized, so that we can train a neural network faster with less data and all that. And then, so that was about one perceptron. But once you have all that settings, all that set up for your neural network, what you can do is you add layers of neurons. So it's not just about, so you have your inputs, but then it's not just one perceptron that all of these information goes to. It's different perceptrons in each layer. And then it's also layers and layers of computation that make a neural network. And then I guess you can imagine that the main question here is, we have those weights that are those knobs that indicate how important features are and how the output is made based on the input and all the features that we have. And then the question is, how does the neural network learn to find the right weights? And the answer is an algorithm, mostly, like in most cases, an algorithm called gradient descent. So gradient descent is an algorithm or a method for updating the weights to minimize the cost function. Because if we have the right weights, then we can say our neural network has learned, and it can find the patterns in our data set. So how usually a neural network works is that we randomly initialize weights, because at the beginning, we have no idea how important each feature is and how, based on the information that we have, what the pattern is. So we start randomly. We choose a random starting point. And then what we do is we go through a forward pass. So that would be calculating the output based on the current weights that you have. And once you have the output, you can calculate the loss function. So you can see how much the predicted output is different from the desired output in your data set. And once you have that, now you have to decide how to change the weights so that loss is smaller. And there is a measurement for that can help you. It's called gradients. So gradients, you can think of them as slope or like the direction in which you can go so that your cost function is minimized. So it kind of measures the change in weights with respect to the change in the error. So it can tell you how you should change your weight so that your error or loss or cost is less. And then once you know how to change your weights, you have to decide how fast or how big you want to change those weights. And we call that a learning rate, which decides how fast you want to make changes to your weights. So here is a visualization of how that process might work. On the y-axis, we have the loss, and on the x-axis, we have a weight. This is a very simplified intuitional version because as you can imagine, you don't have just one weight. Like it's not just a number, it's like matrices at different levels of the neural network. But in general, the idea is that you have the weight, and based on the weight, you can calculate the cost, because based on the weight, you can calculate the output. And once you have the output and the real expected output, you can calculate the cost. And then you start somewhere randomly. And the goal is to get to a point where cost is minimized. So you need to take steps to get there. And to get there, gradients can help because it can show you the direction to which you should move. And a learning rate can help, which can tell you how big of a jump you want to take to get there. And once you get there, and we call each of these like jumps a training iteration where the model is being trained on your data, you're all good. And you're at the minimum of the loss function. Your neural network is doing the best that it can, hopefully. So once you have the gradients and learning rates, it's time to update the weights. Hopefully, they will get better and the loss will be less in the next iteration.
Sorry, Golnaz, before you move on, there's a question in the chat. Can activation functions be changed dynamically based on patient characteristics?
So in general, you can change activation functions, but so the general practice is to define your problem, fix your activation function depending on your problem, and then what you try to change to make your network better is just the weights. So when we talk about training the model, or when the model is learning from like data from different patients, it's actually just updating the weights and activation functions are fixed. But there is also research on the not traditional ways of training neural networks, where they try to fix the weights and instead change the activation functions based on the data that's coming. And the data could be like data from different patients. And the goal is for the model to learn the pattern, for a general pattern for all the patients, right? So there is like research being done on that, but that's not the general way to do it. So the general way is to fix the weights, fix the activation function, update the weights. Oops. So yes, as a summary, so that's how to train a neural network. You just have to update the weights and optimize them so that the loss function is minimized. And how you do that is by calculating the gradients and the learning rate. And it basically means you're deciding how fast to change the weights and also the direction to change the weights in order to minimize the loss. And as the loss gets smaller, you don't have to make big changes anymore, and the gradients also get smaller. So at the beginning, you're expected to make big changes to the weights of the neural network, but as the neural network learns, the weights change less. And once you have a loss that is small enough, you can say that training is enough and your neural network has learned. And once you have that, you can fix the model, use it on new patients and data from other resources. But the problem is that it's not as simple as that. And by that, I mean, it's not as simple as this plot here, where we have a minimum here in the middle and we start at the top and we get there. It's usually much more, it's much messier than that. And by that, I mean, we're in high dimensions, and it's not just a minimum that we want to find. There might be multiple minimums. So the question is the minimum that we're finding good enough or not? Are we at the best, or can we do better? Which are all optimization questions that mathematicians and computer scientists try to answer. But in general, there are solutions to that as well. For example, learning rate is one of the things that, as a designer of a neural network, you can control. So it's your choice of how fast or small, how big of a step or small of a step you want to take. If it's too small, it will take too long to get to the minimum, but it will be more stable. On the other hand, if it's too big, it might skip over where you want to get. So we call it overshooting, or we call that the model or the algorithm has diverged. So what happens is that you're setting your learning rate too high. So you're training your data, training your neural network on your data, and you see that the loss is not changing. So you're changing the weights, but it's not getting better. And you have to figure out what to do. So one potential reason could be not choosing the right learning rate for your problem. So again, there are solutions for that. We call them optimizers. So optimizers are basically smarter ways to decide how to change the learning rate over time. And by time, I mean the training time as we go through the data in the data set, to make this process easier and more smooth. So one technique is learning rate decay, which is basically starting large. So taking bigger steps at the beginning where the problem is, where because the weights are random, right? So you know that the thing that you're predicting is probably making no sense at the beginning. So the loss is large. So you need to take big steps at the beginning. And as you go down, and as time passes, you can make the learning rate smaller. So there are all these details about neural networks that, as a person who is designing them, or as a person who is reading a paper about them, you can think of. And I just have like the name of some of these optimizers or decay functions here as reference. And for each of them, like there is a paper explaining why it's better to do that, and it makes the training process faster. So that was about the general training process, but there are also a lot of design choices that you need to make along the way when you're designing a neural network for your problem. One of them, as you saw, was learning rate. There's also the choice of loss function. So depending on your problem, your cost or loss function might be different. You also have to decide how many times you want to go over the data to learn from it. That's called an epoch. You also need to decide how big your neural network should be. Should it be deep? Should it be wide? Should it be shallow? So these are all the questions that people who study deep learning try to answer depending on the problem. So as a summary of how a neural network works, you can think of it as the first step is, and I think you can think of a neural network like the main part of a neural network is the weights of the neural network. You can kind of think of it as in a brain as well, where the connections between the neurons matter and how they store information and memory and how like changing those weights and which are the connections between these neurons uh, uh, make learning different, or it can cause it can make you learn something or unlearn something. So how the neural network works is it is randomly initialized with some weights because we don't know how the problem is solved. And to solve the problem, we go through training iterations, which is we take a couple of data, we calculate what the output of the neural network is based on that input. And once we have the output, we can calculate the loss. And once we have the loss, we can do the backpropagation or do the gradient descent, where you update the weights depending on how the loss changes. And then you go through this process a couple of times, and you do it over and over. And in each iteration, you measure how well you did it. So you measure the cost or loss function, and your goal is for your model for its loss to be at a minimum. And once you have that, you kind of have solved your problem. And you might go through this process and it might not work. So if that happens, that means that probably hyperparameters for your problem were not chosen carefully. So you need to have another process of choosing the best design choices for your neural network as well. And once you have that, once you have your loss at a minimum, your weights are optimized, your model is trained, and it's ready to use. Okay. So with that introduction, just a question to check if these words make sense. So just as a summary, we had perceptrons, which were the main computational units. Then we had the activation functions. We had the loss function, which indicated how well the model is doing, the neural network is doing. And then we had a lot of design choices, like the number of layers, the learning rate. So that's true. Activation functions are mainly used for adding nonlinearity, but there are also computational units so we call them normalization layers, and their goal is to normalize the inputs. Because you can imagine that if here in your model, if one of these inputs is much bigger than the other input all the time, that can kind of bias your neural network to learn something that it's not supposed to. Okay. I think I have another question here as well for. So the question is, these are the steps to training a neural network, and let's order them in the right order. Okay, that is correct. So random weights at the beginning, calculating the output based on the output and the expected output, you calculate the loss. And now that you know how far off from the actual ground truth you are, you can update the weights so that you're making better predictions. So here I have an example, and mainly I have it here as an excuse to introduce you to Kaggle. So Kaggle is a place where people put their data sets that they've collected and ask other people to solve them. And they can use any machine learning method that they think would be a good fit for the problem. So it could be what you've learned before in the previous lectures, like k-nearest neighbors, random forests, or neural networks, and like what kind of neural network is also another question. So in particular, there is this data set here on heart failure, where they have their data set and their explanation. So it's basically they've collected data on people, and it's different information. So age, if they had anemia, if they had diabetes, and a lot of if they smoked. And then so these first columns are called the features of the problem, and then the last column is the death event, if the patient died and they had these characteristics. So you can think of this as a problem that a neural network can solve, right? And how that would work is once you have trained your neural network on your data, what you expect your model is you give one of these rows of this data set to the neural network. So it would be the information for a patient. And then you want the neural network to predict if the patient will have heart failure or not. I also want to point out to some kind of like computer engineering subtleties here that does all have to do with numbers. So you can see that these numbers are at different scales, and something you have to do and you have to keep in mind is also to have them at the same scale. For example, have them standardized before feeding it to the neural network or train the neural network on it. And then once you've done with the training, with the process that we talked about, you hopefully can make a good prediction. And I also want to mention that here we have a box that's getting the input and giving you the output. The box here could also be other algorithms that we talked about in the previous sessions. And in particular, for example, since it's a classification problem, because what you want to predict is a binary yes or no, if the person died or not. For classification, you can use models like random forest or boosting or bagging methods. And even in some cases, it's better to use them rather than a neural network, because neural networks usually perform better if you have more data. And if that's not the, and you can imagine why, because you have to go through this rigorous process of training and changing the weights. And in each step, you're making just small changes. And for the next step, you need new data to make new changes to your weights. But that's not the case for many of the other algorithms, like the more traditional ones. So if your data set is smaller, neural network might not be a good choice, but okay, so we talked about training the model, and we talked about once the model is trained, now you can use it for making predictions on the new data that's coming. But one step is missing here, and that's evaluation. So before deploying your model, you need to make sure that your model is good enough. And to do that, to do the evaluation, the general process is to, so first you end the training, and then so ending the training means no more updates to the weights. They're also called parameters in some literature. And then once you fix the weights, you choose a metric to report how good your model performs. And then you prepare a new data set that your model has never seen before, and you report that metric on that unseen data set. So this whole process is usually to avoid overfitting, which is a scenario where your model performs great on the data that it's seen before, but it can't perform well on the data that's new. So it can usually be a sign of the model just kind of memorizing all the patterns, but some of those patterns might be spurious or not actually real, or they could be just noise in the data. And that's something that we don't want. So evaluation is also a very important step of using neural networks for any application. And again, the metrics, depending on your application or like the problem that you have or what you care the most for your problem, can be different. So it could be accuracy, it could be how different the output is from the expected output, which would be in regression cases. So back to questions about evaluation metrics. Do you know any evaluation metrics when you're using prediction models for medicine? Area under the curve, precision, exactly. Exactly. So I think that you might have heard about them in other courses like that deal with statistical data, but or like like general statistics. But for example, for a classification problem, one of the things that you can use is a confusion matrix, which indicates of the predictions that you've made on your data set, how many of them were actually from the same class that the model predicted. And then how many of them were predicted as the other class. And you do it for all of the classes that you have. And then based on that, you can measure different metrics like precision, recall, F1 score. And depending on your problem, for example, if your data set is not balanced, for example, in when you want to predict cancer, for example, you will have one sample of cancer probably and a lot of samples that are not cancer. And then you need to define a metric that takes into account that imbalance. So like the usual accuracy metric might not be useful. So you could use some of these metrics that are proposed. I have this neural network playground here for you guys that you can play around with later, which is basically you can choose your data, your problem. So for example, this one is you have these orange dots and blue dots and you want to separate them using a neural network. And you can play around with all of these design choices of how fast you want your network to learn, what activation function, how many layers in each layer, how many neurons, and then you can hit run and see if your model can learn the pattern or not. And if not, you can play around and see why it's not learning. And it also shows like, so these connections are the weights. So like larger connections means bigger weights. So you can kind of play around and see how a problem might be harder. For example, adding noise makes a problem harder. And all the other design choices of a neural network, you can also play around with that.
Golnaz, a question. For evaluation, does the new data set need to be real world data or can it be generated by another algorithm?
That's a good question. So it should be data for which you have the label, and it also should be like it should be completely like the same features, whatever you've collected in the original data set. I have not seen people using synthetic data for evaluation. What they usually do is they if you, for example, if your problem is you don't have enough data, you definitely might need to generate something synthetic data, right? And what they do is uh, they they generate it on the whole data set and then use it for both training and testing. Like then at this case, like in this case, there might be synthetic data both in your train set and your test set. Okay. So I think this is a summary slide of the training neural networks. So you choose the details of your neural network architecture. So it could be the choice of activation functions, how you want to pre-process your data, how you want to initialize your weights randomly. And then you go through the learning process of updating the weights to minimize the loss function. You might also need to do some hyperparameter tuning. So that would be adjusting the knobs of your neural network to make it well suited for your problem. And then once the training is done, you need to evaluate your model. So that would be defining an evaluation metric and then measuring how well your model does on unseen data. Okay. So this was the first part, the fundamentals of neural networks. Should we have a short break and then go to the applications?
Yeah, I think that'd be good. You think 5 minutes is sufficient or?
I think so, yeah.
Okay. We'll reconvene at like 6:02 then.
Okay. So with that, let's get back to Menti for a question on evaluation of. So the question is, why do we evaluate on a separate test data set? Okay. Yes, to see how the model performs on unseen data. So performance of the model on unseen data, that's not completely different, and it's still from like the same problem, but it's slightly different from what the model was trained on. It's a big topic in machine learning and deep learning in general. It's the topic of generalization. So the question is, can your model generalize well to unseen data? And neural networks are shown to have good generalization in most of the cases, and especially if you make them if you have more data and you have a bigger model for your problem, which basically means that it has more capacity to store information and find more complex patterns in the data. But that's still one of the ongoing topics in machine learning and evaluation of these models. So with that, let's move to the next question, which is about. So we talked about the fundamentals of neural networks, now their applications and the neural networks designed for those applications and different kinds of data. So the question is, what are some examples of imaging data in medicine that you know of? Ultrasound, MRI, OCT, PET scans. Histology, heart ventricle sizes, X-ray. Yeah, exactly. So there are many different kinds of data. What's the new one? EEG, ECG. Yeah, X-ray. Thank you, guys. So yes, as you can see, like there are many different sources of data that are in the form of images, like ultrasound, MRI, CT, PT, and different fields in medicine where those images can be helpful, like pathology, dermatology. So the question is, if I have an image, or if I have a big data set of images and I want to find something in those images, can neural networks help? So I want to start this section by where actually the research on neural networks, on convolutional neural networks, which are the kind of neural networks that are used for images, started and was kind of inspired. So it was actually inspired by some experiments that was done on cats, and I also think monkeys, where they would record, they would make some recordings from the visual cortex of these animals while they were showing them some visual stimulus. And so they would change the stimulus and they would measure what's being activated in their brain and what's the pattern there. Like if you change the shape, if you have the same shape but in a different place, in the screen, how does that change the what happens in the brain? So what they found out was a couple of things. The first one was hierarchical feature extraction. So that means that neurons in lower layers, they detect basic features like edges or lines, and then as you go deeper in higher levels, there are neurons that combine these features to recognize more complex patterns and shapes. So that's one thing that they recognized. Another thing was translation invariance, which means the ability to detect features regardless of location. So how you can find a particular feature is invariant of where that is located, which is an important characteristics of how we process visual information. So in particular, in a brain, there are specialized neurons and group of neurons that are tuned to detect specific types of features in the visual input. So the question is, can we have kind of the same thing, like some computational process that is specialized, that is tuned to find particular patterns, and you don't want them to be like, you don't want to define those patterns. You want to learn them as the data comes, like from the data, not by defining a rule of what an edge means, but by learning what an edge means from the data and by seeing multiple images of edge or a particular shape. So in CNNs, or convolutional neural networks, which are neural networks designed for processing images, we have kind of the same idea. So there are small trainable computational matrices that can scan across an image, and they can detect patterns like edges, textures, colors, stuff like that. So why don't we want to define what an edge is to the model? So that would be a more traditional machine learning, or like pattern recognition in general, where they would try to like define those things as rules, or as like, so it would be something a human would define what an edge is, or like what a particular shape is. But the problem is, no matter how detailed your definition of an edge is, there will be an edge that's not in your definition, probably, and that will make it hard. So the hope is, instead of just defining every rule for it, just have like a data set as big as possible and hope to learn it from data. And to learn it from data, you need good structures that can just go over all those data and find patterns and store those patterns in the form of, for example, matrices or any sort of information, for example, in the weights of the network. So these small trainable matrices are called filters, which are matrices that go through an image. They scan the image, and again, they're kind of like the weights of the neural network that we learned previously. So they, like these filters, they start like, you can just initialize them randomly, and the hope is to learn the filter. So to by going through different images and updating these filters based on the images, you can find, eventually you can have a filter that can, for example, detect an edge. And it's also interesting that the same kind of hierarchical features extraction and hierarchical learning also happens in these kinds of neural networks. So in convolutional neural networks, which are deep neural networks, and their building blocks are convolution layers where those filters go through the images, and the image is the input to these networks. And then, for example, you want to predict if the person has breast cancer or not. As we go through the layers of the images, they start with learning low-level features, these filters, and then as we go to the deeper levels, more complex patterns are learned with these filters, which is an interesting observation. So those experiments kind of inspired the idea of CNNs, and like seeing how the brain processes visual information could give inspiration to designing tools that can process information in kind of the same way. So you can imagine that CNNs can be useful when your data has a spatial temporal dependency. For example, it's not like a table where every row is completely separate from the other. In each image, there are like spaces in the image that are correlated with other spaces. So like things being close together means something in an image, and you need a model to learn that learn those patterns. And CNNs are one of the suitable models for these applications. I also have to mention that, again, as any neural network, they also come with a lot of design choices or hyperparameters. Like we talked about filters, so you have to decide how many filters you want to use in your CNN, or like if you want to make changes to your image, for example, add paddings to your images to make computation easier based on your problem. So that's something to be careful about as well. But in general, like this is an kind of a good visualization of how a convolution layer would work in a CNN. So you have your image, which is, you can think of it as a matrix where each of these numbers are like kind of defining the color that is in that pixel. And then you have your filter, and that filter goes through your image. So we call that like this kind of like going through the data convolution. And then you make you kind of multiply these two matrices together element wise, and then you will have your output. And then once you have your output, then you need to at the end, what you want is not a matrix, but you need a number as your output, as the output of your model. So you need to downsize what you have, because, for example, the output of your network is a 0 or 1, which would be the yes or no of if the picture, if the image means the person has cancer or not. So there are like other layers that do that that are called pooling layers, which go through the images. And for example, here is a max pool layer where at each of these like 4 numbers, it picks the maximum and then keeps that. So again, these are all computational units of these systems, and also a lot of research on how to make these computations better or use better functions here. And as you can see, there are a lot of applications. The applications are usually called classification or image segmentation. So image segmentation is basically a classification at a pixel level. So for example, you don't want to give the input, so you don't want the input to be the image and the output to be a yes or no, but you want that yes or no to be on the pixel. So you want to see which regions, for example, the tumor is. So that would be a segmentation problem. So depending on how you define your problem, again, the way you have to process your data and define your model would be slightly different, but the general idea is the same. So you need to learn from data. You need to use convolutional neural networks, which basically learn filters that can kind of define the patterns in the image. Any questions up till now? Okay, so with that, let's see what the next question is. So the question is, why is translation invariance especially important for CNN in medical imaging? So as a reminder, the word means if the same object is in different places in an image, you still need to detect it. And yes, that would be the third option. Okay. So that was about images. The second part is temporally correlated data. So data that is correlated through time. So my question is, do you know any kind of time series data in healthcare that either you had to collect or you saw a project that used that data to make a prediction? So survival data, EKG, air pollution data, COVID cases, treatment responses. Yes. Yeah. They're very good examples. Yeah. Yeah. So again, there are many cases where data is not just a CSV file with numbers. It's or it can be a CSV, but what it means is like each row is not independent of the other. It's gathered through time. For example, electronic health records, EEG, respiratory rate monitoring, physical activity monitoring, blood glucose monitoring, medication dosage. And again, you want to make prediction and diagnosis tasks on these data. So in the next few slides, I'm going to go through the neural networks that are particularly designed for temporally correlated data, starting from the first models that were introduced. So recurrent neural networks, then a model called long short-term memory, gated recurrent units, attention units, and transformers. And but before that, I want to also mention that working with time series data can have a lot of challenges too. Like there could be irregular time intervals. So for example, irregular visits of the patient. So you need to figure something out for if the data is irregular. For example, you have missing points, missing columns in your data set. How the data is high dimensional, and usually like it's large volume. For example, for each patient, you have a lot of data because it's a time series over it's over time collected. There's also this problem called non-stationarity, which is things changing over time. So you either need to kind of formulate that non-stationarity or make sure that your data that you have is as stationary as possible. So there are all these challenges when you're working with time series data as well. So starting with the first type of neural networks that were designed for time series data, RNNs. So on the right here, I have a kind of simplified version of a perceptron where you have your input and then you get your output. And then like this green box here will make some computations on the data. But it basically just receives the input at a particular time step and then gives you the output. The idea of the RNN is that the result is going to depend also on the previous history, so the past memory. So it means that you have the input vector, but you also have the output from the previous step as your input. And then based on these two information, you can calculate your output. So it's kind of giving you, because you're using the previous outputs of your data, you're kind of giving your model some information about what happened in the past. So it's not just one point in time, but it's a kind of a history in time. So that would be an RNN, and we call that structure sequential memory because RNNs then have a hidden state, so that would be information about the past and what happened in the sequence. So historically, there were some issues with how these networks would be trained. The problems were called gradient flow problems, which is those gradients where you use them in each level, in each like training step to update your model. If they get very big or very small, what happens is that you might lose your ability to learn over time, because those computations get very big or very small, which make no sense anymore. So that was one problem, and it also couldn't learn patterns about long-term memory. So after that, and because of that, long short-term memories were introduced, which were kind of a solution to those training problems for RNNs, the vanishing gradient problems. And what they used something called gating mechanisms. So that would be adding some more computation parts to, for example, forget some part of the data. And that helps with the problem. After that, and kind of one of the things that revolutionized deep learning models was attention mechanism. So basically, in RNNs, what we did is we used just the previous step as the new input to the model, so that we could use the information in the previous step. But still, what if what is happening right now doesn't depend on just the previous step, but also what happened 100 steps ago, and it's just showing up now. So what attention does is that it uses all intermediate states, not just the last one, for generating the output. And so it basically means just paying attention to all of the past and like weighting, like assigning importance to different points in the past, not just the previous step. And that would help with the long-term memory loss problem in the previous models. So based on that, and just taking that and adding some kind of engineering tricks and like parallelizing the data, transformers came, and it's basically a much more complex model, which includes what they call an encoder and a decoder. And I don't want you to memorize these names, but it's basically just saying that taking like going through all those improvements and like adding to them and coming up with better computational parts so that you can make sense of time series data. So that would be an overview of how models were designed to deal with temporally correlated data. I also want to mention that each of these applications that we're going through, they could be a separate one full semester course of machine learning on just that topic, where you could just, for example, study transformers and how they work and how you can make them better, or like to implement them or use them for your problems. And the goal here is not to do that. So what I'm hoping is the next time you're reading a paper and you see one of these names, you can kind of track back of why they used that model and what other options they had and what are the space of solutions based on your problem. And hopefully that would be helpful. So the third application of neural networks is when you, for example, don't have enough data, or for some particular reason, you want to generate data or augment data. So imagine you have a data set, but you don't have enough data, but you also know that if you make small changes to your data, the model can learn slightly different things in a slightly more generalized way from the data. Some non-machine learning methods that like some not algorithm methods that you can use is just simple stuff like just rotating the image, flipping the image, changing the brightness, adding noise to the image, which could then firstly add more samples to your data set, and second, your model can learn slightly different things from each of those images, which could be helpful with the generalization problem in the neural networks. But there are also some machine learning and deep learning methods that you can use to do the data augmentation. An example is generative adversarial networks, or GANs. So how they work is that they are made of two main parts. The first part is generator, and the second part is discriminator. And the job of the generator is to generate fake images. And then the job of the discriminator is to detect those images and flag them as fake. And these two play a game together. And at each iteration, the generator tries to generate the best image that it can that's fake from random noise. And then the discriminator's task is to discriminate between real and fake. And through this game of just interacting with each other, these two modules learn to generate fake data. Another group of models that are kind of more new and trending now are diffusion models. For example, those models where you can type something and then it can generate an image for you. Many of them are, like, part of them is the diffusion model. So how a diffusion model works is that their task is also to generate data, but how they learn to do it is that they learn to diffuse training data with some random noise and then learn to reverse that diffusion process to get new images. So it's basically, you have your image, you slightly add noise to it until it's not recognizable, and then you learn to reverse that process back. And if you learn that whole thing, then you can generate new images that look like the actual images. So here, for example, in the plot, I have like some synthetic histopathology images generated by one of these models. Some of the use cases for these generative models are, again, when you want to generate an image, you need more data, or if your task is image reconstruction. For example, part of the image is broken, and you need to figure out the best way to generate a new image that reconstructs that part of the image. There's also applications on denoising and anomaly detection using these models. And in general, like having a little bit of data from these generative models in your data set can help the fairness and generalizability of your model, for example, of your medical classifier. An example where when the first time I was learning about generative models, I heard about on how they can be helpful is, for example, when you want to take these medical images of babies, and it's hard to like it's hard for them to sit, and like they might move, and the image might be noisy, or you might need to reconstruct the image. And if you have a model that can do that could be helpful a lot. Or if your data set is not complete, that could help you a lot to use these generative models to add to your data set as well. Okay. So that was about the third application, the generative models and data augmentation, data generation. The fourth one is neural networks for text and language data. So an example that you might all know is ChatGPT. So getting back to the Menti, my question is that do you use ChatGPT for clinical support or when you're thinking about a medical problem? And are you comfortable with it, or are you comfortable doing that or not? Okay. Okay, kind of not evenly distributed, which kind of shows how controversial it can be to kind of integrate these tools into our daily lives. So you might have heard of ChatGPT, but ChatGPT is a model that, or many of the large language models are models that sit under the umbrella of foundation models. So foundation models are different from the usual definition of neural networks in the sense that they are usually trained on very large and very diverse data sets, and even from different modalities, or like different, for example, data could be both image and text and video, so coming from different sources. And then they're also trained using a process called self-supervised learning, because you can imagine that if you have a data set that is too big, it would be really difficult to do the labeling for every row in your data set or for every image in your data set. So what you can do instead is to teach your model to learn the information that is already in the data set. So that could be, for example, learning to predict missing or masked parts of the input, or to discover patterns, or like find which samples are similar to each other, which samples are different to each other, if you don't have the exact label for everything. So it's a bit different from supervised learning, which were all the things that we talked about today was supervised learning, like in classification or regression. In your data set, you already have the label from wherever it's coming from. Like it could be from a clinician, or it could be a measurement, but you know what you want to predict and you want to teach the model that. But here in foundation models, since that's kind of not feasible, we try to redefine the task and teach the model to find patterns. So how they work is, you might have heard of these steps of, or like these buzzwords of how foundation model works, but so in general, it's usually 3 steps of first pre-training the model, which is kind of like it's basically training, which is learning the general patterns in these large and diverse data sets. And then once you're done with the pre-training, you have a general model that might be useful in many general applications, but you might need to adapt your model. So that would be another step of training on your specific task or your specific problem to make your model fine-tuned and well-suited for your particular problem. And once you do that, if that's not enough too, there's this step called alignment, where, for example, you can give the model feedback and the model can learn from your feedback, and your feedback should show how aligned the model output is with what you want or what you value as the output. So that's the basic difference, and here is a visual of an example. So it could be a really large model. So and by large I mean like many layers and therefore weights. So the network is big enough and has the capacity to learn a lot of information, and you have data from different places. And once you have that, then you can use it for general application. And once you train your model on data that's like image, audio, text, there are different applications. Like it could be a chatbot, it could be note taking, it could be making a radiology report based on the image. And you can also think about how each of these tasks can also be broken into smaller tasks. So another like research problem is all of these tasks that we're trying to make the foundation models work on, many of them are very long horizon, meaning that you have to make a sequence of decisions to get there. So how can you do that? And how can you make models that are better at sequential, like kind of planning in a large, when your problem is not just a one step yes or no, but it's more than that. And you can imagine that there are also pros and cons to these models, since they are trained on big and diverse data sets. They can be used for many general purposes, and they can also be adapted to a wide range of tasks. And they're shown to have higher accuracy on many tasks. But there's also a lot of problems. For example, the data that you've collected to train these models, how correct are they? And if there are biases in the data, how are they reflected in your results? And also, since these models are big, there's a high computational cost to them. And another thing is that these models can make errors. So they call those errors hallucinations. And that's also a limitation and something that computer science people are trying to fix. So that was about foundation models and text and language data, and in general, like these big models that are good in doing many different tasks. Another application of neural networks is for graph structured data. So we'll get to what that means. So sometimes your data is not a table, it's not an image, it's not a text, but it's kind of a set of relationships and a set of connections between different concepts or between different entities that you have. So it has a relational structure where concepts are connected to one another. So you can think of it as a graph where concepts are the nodes, and then those connections are how those nodes are related to each other, and we call them edges when we're studying graphs. And then if you can define a problem where you want to find something out about this relationship in a graph, then you can use a graph neural network. And this would be a graph representation of the data where you need a specific kind of neural network that can process that information in the form of a graph. So in particular, for this purpose, graph neural networks are used when data is naturally represented as a graph. And some examples of how data can be represented as graph is, for example, molecular structures of drugs could be represented as graph, for example, in drug discovery. Or if you want to find drug-drug interaction networks, that could also be represented as a graph. For example, if you want to see how a new drug might affect another drug that a person is taking. Or even other examples out of like pharmacy, like how cell systems are organized, that could also sometimes be represented as a graph. Or like gene interaction networks. So any problem where you can formulate your problem as a graph, your solution should be a graph neural network, which has like those specific computational structures to process data in the format of a graph. So with that, I have an example here. So here, the example is drug-protein interactions. So think of like if you had a problem or if you had a data set of drug and protein interactions, what would the nodes be, and what would the edges or what connects the nodes be? So think of the problem as you want to predict how a drug will affect a particular protein. And then you have a huge data set of other drugs or similar drugs and other proteins and similar proteins. Yes, so the nodes would be the drugs and proteins. So they would be two different kinds of nodes. And then the edges would be the interaction between each drug and each protein in this case. So yes, that's an example of a problem that could be represented as a graph representation, and then you could use that data to train your model. And then, for example, you can ask the question of what if I have a new drug, and or like even like the interaction of two drugs, and then taken together, how can that affect something about proteins? And then you have all the information about the previous things that you've discovered about the drug and protein interactions. So we learned about graph neural networks, convolutional neural networks for images, foundation models that work with different modalities of data. It could be image and text and other stuff. We learned about time series data and RNNs. And I also want to mention that you can also mix and match these components. So your problem might be big enough where you need some modules to extract some information about the image, and then you need some modules to extract some information about the temporally correlated part of the problem, or even your data set might come in different modalities, and at the end you want to predict something based on an image, and also some notes of or some measurements about the patient. So the key point is to know your data and also know what solution you have for each kind of data, and also there are methods to kind of connect all these solutions together so that you can have a model that can make the prediction for your problem. Okay, back here. So the question is, we learned about different models. Here are a bunch of models here, like as the solution, like CNN, foundation models, linear regression. Which one would be useful for example, summarizing a patient's clinical notes? Yes, so large language models are particularly designed for doing tasks like summarization of a text. I just want to check. Okay. So I'll get back to the attendance and feedback where Yin can talk about it. But just as a summary, we talked about the fundamentals of how a neural network generally works. You have all those features where define your problem, and then you have the weights, which indicate how important those features are and how they're related, and their relationship together will make a prediction. And then you start randomly with the weights, you make a prediction, you double check it with the actual value that you wanted to predict, and you calculate the loss. Based on the loss, you can update the weights, and then this process is done over and over again until your model is trained. And then once your model is trained, you need to evaluate it, and then it's ready to be used for your problem. And then depending on the data, there are different solutions, different models, and each of them you can learn about, like, and if you need resources, you can reach out. But basically, they're designed with their own computational units for a particular application and a particular form of data. And so depending on the data, you choose your model, and then your knowledge as medical students can be fundamental for defining the problem, for formulating the machine learning problem. For example, at the first step, indicating which features even to include in your data set, or like for finding the right labels when you're preparing your data set, so that the machine learning algorithm can learn from the supervision of a medical expert. And then once you do that, these models can help with individual clinicians in making decisions, in general, in public health planning, in making big decisions about the next step, about taking action, and then also with the general public, for making their lives easier, hopefully. And then you should be careful about evaluation of these models, knowing about biases and risks. And Aslan will talk a bit about biases and risks in the next sessions as well. And then once we have that, these models can both benefit practitioners and patients in a safe way.